everyone, in this video, we will learn about angles in a unit circle. So to begin with, let's review this one. Angle in standard position. This is an angle in a standard position. The initial side is located in the x-axis, the rotation ray is moving counterclockwise, and the terminal side of the angle is located in the first quadrant. This is an example of a positive angle. Another. This one is still an angle in standard position. The initial side is located in the x-axis, the vertex is the point of origin, the terminal side is located in the fourth quadrant, and the rotation ray is moving clockwise. This is an example of a negative angle. So take note, if the rotation ray is moving counterclockwise, it is a positive angle. If it is moving clockwise, it is a negative angle. So therefore, with this one, an angle in standard position is an angle with a vertex at the point of origin, and the initial side is always at the positive x-axis. Take note of that. Central angle is an angle with its vertex at the point of origin and its sides are radii of the circle. Now, this one is a central angle. The radii here are sides of the angle, and the arc length here is the intercepted arc of the given central angle. Now, angle RSP is considered as a central angle in as much as angle RSQ is also a central angle. Now, take note, a central angle measures 1 degree if it intercepts 1/360 degrees of the circumference of the circle. Now, take note, 1 degree is 60 minutes and 1 minute is equivalent to 60 seconds. Now, take note, an angle measure could be in degree, minute, and seconds form. Now, let's convert this to degree form. Now, take note, this is 10 degrees. 30 plus 18 seconds is just the same as 18/60 minutes. Now, simplifying this, we will have 10 degrees and 18 divided by 60 is 0.3. So that would be 10 degrees and 30.3 minutes. So since this is still minutes, let's convert this to degrees. So that would be 10 plus 30.3/60 degrees. So simplifying further, we will get 10.505 degrees. Now another. If it is degree form, let's convert this to degree, minutes, and seconds form. Now this is 79 degrees. Quantity 0.251 times 60 minutes. So that would be 79 degrees. Multiplying this, we'll get 15.06 minutes. So let's convert 0.06 to seconds. So that would be 79 degrees, 15 minutes, quantity 0.06 times 60 seconds. So simplifying, the final answer would be 79 degrees, 15 minutes, and 3.6 seconds. Take note of that. Okay, next. Now, angle measures could be in degree form, it could be in radian form, or it could be in rotation form. Now, take note, one complete rotation of a circle is equivalent to 360 degrees. And 360 degrees in radians, it's equivalent to 2 pi. Or one complete circle is equivalent to 2 pi. And that is in radian form. Now, if it's only half of a rotation, so meaning it's a semicircle, so degree form to that would be 180 degrees, and of course the radian form would be pi. Now take note, in trigonometry, pi is equivalent to 180 degrees if we're talking about angle measures. Next, If the degree form is 60 degrees, then its radian form would be pi over 3. And the rotation here would be 1/6 rotation. Next, if the radian form is given as 3 pi, then equivalent degree form for this would be 540 degrees, and the rotation here would be 3 halves rotation. So meaning it's 1 rotation plus half. Now, how to convert angle measures? Now, to convert from degree to radian, so for example, 60 degrees, our conversion factor would be pi over 180 degrees. So 60 by 180 degrees, we can have this 1 over 3, so that would be pi over 3. Next, to convert from radian to degree, we simply substitute pi by 180 degrees. So for example, pi over 3, convert this to degrees, so pi would be 180 degrees over 3, we'll go back to 60. Another, to convert radian measure, meaning in length, to degree, divide the radians by pi, then multiply by 180 degrees. Now, for example, 4.28 radians, so that would be times 180 over pi. So 4.28 times 180 degrees, divide by pi, then use degree, minutes, and seconds form in your calculator, you will get this value. Now, take note. Example, convert 80 degrees to radian form, so that would be 80 degrees, so pi over 180, so 80 by 180 is 4 over 9, so 4 pi over 9. Another example, convert 2 pi over 3 to degree form, so that would be 2 pi over 3, so take note pi is equivalent to 180 degrees, so multiply divided by 3, you will get 120 degrees. Another, convert 3 pi over 2 to radians in length. So with this, that would be 3 pi over 2. So 3, our pi here would be 3.14 over 2. So we will have 4.71 radians. Take note of that. Another, convert 2.5 radians to degrees. So to do that, 2.5 times 180 degrees divided by pi, then you press degree, minutes, and seconds in your calculator, you will get this value. That's how are you going to do it. Another. Now take note, 1 complete rotation is equivalent to 360 degrees, is equivalent to 2 pi, and it's equivalent to 6.28 radians. Take note, this 4 values here would mean the same thing, meaning that's 1 complete rotation in a circle. Take note of that. Now, let's have this. So, 245 degrees, convert this to radians. So, 245 over pi over 180, you'll get this. And to get the radians in length, that would simply be 49 times 3.1416 over 36, you'll get this. Now go back. What is the difference with radians pi and radians in length? Now when you talk about radians as pi, so the value here is 180 degrees. So meaning you're referring to angle measures. But when you talk about radians in length, the value of our pi here is 3.1416. Take note of that. Okay, next, 21 pi over 4. So convert here. That would be 21 times 180 divided by 4. You'll get 945 degrees. And convert to radians in length. So 21 times 3.1416 divided by 4. You'll get 16.49 radians. And 1 radians convert to degrees. So that would be 1 times 180 degrees divided by pi. Press degrees, minutes, and seconds in your calculator, you will get this value. And convert this to radians, you will get 19 pi over 60. Take note of that. Okay, another term is quadrantal angle. So what are quadrantal angles? Now, a 90-degree angle is considered as a quadrantal angle. No? So it's sketched this way. This is the initial side, and the terminal side is the y-axis. Okay, another. This one, 540-degree angle is also considered as a quadrantal angle. So that would mean one rotation, which is 360, plus 180 degrees, so that will total to 540 degrees. Still, 540 degree is considered as quadrantal angle. Another, 180 degrees, 360, 450, and negative 90 degree, they are all considered as quadrantal angles. So therefore, when you talk about quadrantal angles, it is an angle that is in standard position and has a measure that is a multiple of 90 degrees. So take note of that. Okay, another. Okay, coterminal angles. So what do you mean by coterminal? From the word co, meaning together, terminal means end. So they have the same end point or the same terminal side. So if it's sketched, it's easier to identify. For example, 120-degree angle ends in the second quadrant. Its equivalent coterminal angle there is negative 240 degrees. So take note, 120 degrees and negative 240 degree angles are considered as coterminal angles. Another example. This one, a 45-degree angle is a first quadrant angle. So 45 degrees, that's positive. So its corresponding coterminal negative angle would be negative 315 degrees. This is 315 degrees. And another thing is one complete rotation plus 45, that would mean 405 degrees. Now take note, when you talk about coterminal angles, they're angles in standard position that have a common terminal side. Now question, what if the given is not sketched? How are you going to identify its corresponding coterminal angle? So let's have this one. Now, basic rule in identifying a coterminal angle is you just keep on adding 360 degrees or you keep on subtracting 360 degrees. Now, for example, 400 degree. So this is already more than 360. So let's get its smallest positive coterminal. So we will simply subtract. 400 degrees minus 360 will get 40 degrees. So meaning 440 degrees, they have the same terminal sides. Now, to get its negative coterminal, so 400 minus 360 minus 360, then we will end up with negative 320 degrees. Another example. Now, 30 degrees is lesser than 360. So to get its positive coterminal, we add 360. So with that, we will have 390 degrees. And to get its negative coterminal, that would be 30 degrees minus 360 degrees. So it's negative 330 degrees. Another, what if it's negative 60 degrees? So since it's negative, so we keep on adding 360 degrees. And we will end up with 300. And to get its negative coterminal, it's negative 60 minus 360. So that would be negative 420 degrees. Now another, 29 degrees and 10 minutes. So to do this, 29 degrees, 10 minutes plus 360 degrees. So that would be 389 degrees and 10 minutes. To get its negative coterminal, 29 degrees and 10 minutes minus 360 degrees, that would be negative 330 degrees and 50 minutes. Now, what if the given is already in pi or in radians? So that would be 3 pi over 5 plus 2 pi, because 2 pi again is equivalent to 360. So simplifying, we will have here 13 pi over 5. And to get its negative coterminal, we will simply subtract. So subtracting, we will have negative 7 pi over 5. Okay, last example. Now, what if it's already in radians and radians in length? So this would be 10 radians minus 6.28. Okay, again, why 6.28? Because this is just the same with 2 pi or the same with 360. So simplifying, we will have 3.72 radians, and to get its negative coterminal, so that would be 3.72 minus 6.28, which is negative 2.56 radians. So take note. Okay, next, arc length and area of a sector. Now, given this, S is the arc length, R is the radius, and theta is the central angle. Now take note, this arc length here is basically equal to measure of the angle over 2 pi times the total circumference of the circle, which is 2 pi r. So with this, 2 pi and 2 pi we can cancel. So therefore, to find arc length, it's basically radius times theta. And take note, angle here or theta is always in radians. Now, example, find the length of an arc of a circle with radius of 10 meters that subtends a central angle of 30 degrees. Now take note, our formula here is S is equal to R theta. So let's substitute. We're asked to find S. So our radius here is 10 meters and our theta here is 30 degrees. So convert this to radians. So 30 degrees in radians is pi over 6. Now, by the way, class, when you talk about circular functions, you should always deal with angles in radians. So 30 degrees in radians is pi over 6. So simplifying, we will have 5.24 meters. So that is the length of the arc. Okay, another. Area of a circle. So or of a sector. So given this is our central angle, our radius is r, and the shaded part here is the sector. So to find the area of the sector, that would be theta, or the angle, over 2 pi, which is 1 complete rotation. And take note, area of a circle is given as pi r squared. So with this, we can cancel pi and we can cancel pi. So therefore, we will have 1/2 theta r squared. Again, to find the area of a sector is 1/2 theta r squared. So let's have an example. Find the area of a sector of a circle with central angle of 60 degrees and the radius is 3 meters. So let's have this one. So area is equal to 1/2. So theta, or the angle here, is 60 degrees. So 60 degrees in radians is pi over 3. And r squared, or that would be 3 squared, which is 9. So simplifying, we'll have 9 pi over 6, or that would be 4.71 meter squared. Again, when you talk about arc length, the formula is S is equal to r theta, and you talk about area of a sector, that would be 1/2 theta r squared. Okay, next. Okay, now which of this is the biggest pizza slice? So to do this, we will use area of a sector, which is 1/2 theta r squared. So 1/2, 30 degrees is pi over 6. R squared is 10 squared, so 100. So simplifying, it's 26.18 inches squared. Now for this one, That would be 1/2. 45 is pi over 4. 8 squared is 64. And simplifying, that would be 25.13 inches squared. And for the third pizza slice, that would be 1/2. 60 degrees is pi over 3, and 6 squared is 36, and simplifying, this would be 18.85 inches squared. So therefore, among these three, the biggest pizza slice then would be the first pizza. Okay. A jeepney driver has a windshield wiper on the driver's side that has a total arm and blade 10 inches long and rotates back and forth through the angle of 90 degrees. The shaded region in the figure is the portion of the windshield cleaned by the 7-inch wiper blade. What is the area of the region cleaned? So to do this, let's get the total area covered by the 10 inches windshield wiper. Then we will also get the area of the windshield not cleaned, and we will solve from there. So that would be the total area covered by the windshield wiper. So 1/2 theta r squared. So take note, our theta here is 95 degrees, or that's 19 pi over 36 in radians. And our radius here would be 10. So 10 squared. So simplifying, that would be 82.90 inches squared. Next, the area not cleaned by the wiper blade. So with this one, if this is 10 and this one here is 7, so what's left here would be 3. So with this, we will have 7.46 inches squared. Now take note, the total area covered by the windshield wiper minus the area not cleaned by the wiper blade is equal to the area of the region that is cleaned. So with that, that's 82.90 minus 746 would be 75.44. Therefore, the area of the region cleaned is 75.44 inches squared. Okay, next, linear and angular velocity. Let's try to compare and contrast. Okay, when you say linear, from the word line, so it's basically the distance covered with respect to time. So basically, it's linear velocity, which is displacement per unit of time. It's the distance covered with respect to time. And when you talk about angular, so from the word angle, so it has something to do with the number of rotations per unit of time. And in symbol, that would be W is equal to theta over time. So theta here is number of rotations per unit of time. Okay, let's combine this two. So take note, linear velocity is S over theta. And take note, when you talk about arc length is equal to r theta, or radius times the angle theta. So S is just the same with r theta over time. And take note, angular velocity is theta over time. So with this, linear velocity could be r, or radius, times the angular velocity. That's how are you going to do it. Now take note, when you talk about linear velocity, sample units could be meters per second, centimeters per minute, or kilometers per hour. And when you talk about angular velocity, it could be 2 pi over seconds, 360 degrees per minute, 1 revolutions per minute, 1 rev per minute, or 1 radian per minute. So let's have a sample problem. Now, the minute hand of a clock is 12 centimeters long. Find its linear velocity. Now, take note, our linear velocity is r angular velocity, or rw. So let's substitute. Our radius here is 12. Now, how come the angular velocity here is 2 pi over 60? Now, take note, when you talk about minute hand, it will have one complete rotation in the clock after 60 minutes. So take note of that. So again, this is angular velocity, so meaning one rotation per 60 minutes. So that's why it's 2 pi over 60, or you can simplify to pi over 30. So let's simplify. So therefore, the linear velocity would be 1.26 centimeters per minute. Okay, a Ferris wheel rotates 3 times each minute. The passengers sit in seats that are 25 feet from the center of the wheel. What is the angular velocity of the wheel in degrees per minute and radians per minute? And what is the linear velocity of the passengers in the seats? So to do this, let's have this. Now take note, linear velocity is radius times angular velocity. And our radius here is 25 feet. So angular velocity, so how come it's 6 pi? Take note, it rotates 3 times. So take note, that would be 2 pi times 3, so 6 pi per minute. So simplifying, we will have 150 pi. Or that would be 471.2 feet per minute. So to find the angular velocity here, so basically it's 150 pi over 25, or that would be 6 pi per minute, or that would 6 pi in degrees is 1080 degrees per minute. Okay, another example. If a flywheel is 1 meter in diameter, and if a belt over the wheel is rotating at the rate of 1000 minutes per minute, find the number of revolutions of the wheel per minute. So take note, linear velocity is r times w. So let's substitute. Our linear velocity here is 1000. Our radius here, so since its diameter is 1, so that would be 0.5. Then we're asked to find the angular velocity. Divide by 0.5, so therefore, that would be 2000 radians per minute, or that would be 318.31 rotations or revolutions per minute. Okay, another example. A man was jogging on an oval track with radius of 89 meters. If the man was jogging at the speed of 25 meters per minute, what is the central angle generated by the man after 5 minutes? So with this, linear velocity is RW. So let's substitute. Our velocity here is 25 minutes. So since it is asked after 5 minutes, so that would be 25 times 5. So our radius is 89. Then angular velocity is asked. So simplifying, that would be 1.40 radians, or that is 80 degrees, 28 minutes, and 17.76 seconds. That's the measure of the central angle. Okay, next, reference angle. So what are reference angles? So these are reference angles into different quadrants. So this is first quadrant, second quadrant, third, and fourth. So if you can see, the red marking here is a reference angle, and the red mark or the green is the standard angle. In the first quadrant, the reference and the standard angle are just the same, right? So by the way, when you talk about reference angles, they're always acute, and one side is always at the x-axis. So again, going back to the first quadrant, the reference angle is just equal to the standard angle. In the second quadrant, to get the reference angle, that would be 180 degrees minus the standard angle. So 180 degrees minus the standard angle or second quadrant angle. Well, in the third quadrant, that would be 180 degrees, or the third quadrant angle minus 180 degrees to get the reference angle. Well, in the fourth quadrant, that would be 360 degrees minus the fourth quadrant angle. So take note of this. So let's have an example. Now, give the reference angle of the following. So 300 is a fourth quadrant angle. So 360 minus 300 is 60. Next, 250 is a third quadrant angle. So you less by 180, you'll get 70 degrees. And 37 degrees is a first quadrant angle. So therefore, basically, it's simply 37 degrees. And number 4, since it's second quadrant angle, so that would be 180 minus 120, so 60 degrees. Okay, another. Okay, a reference angle is given. You give its corresponding standard angle in the different quadrants. So 50 degrees, so first quadrant equivalent would be 50 degrees as well. So second quadrant, that would be 180 minus 50 is 130. And third quadrant, that would be 180 plus 50, so 230. And fourth quadrant, that would be 360 minus 50, so 310 degrees. So take note, 50, 130, 230, and 310, they are all corresponding multiples in terms of reference angles. Okay, so reference angles of special angles and its multiple. So 30 degrees, so the same thing how we did in the previous slide. So this is 30. This is 180 minus 30 is 150. 180 plus 30 is 210. And 360 minus 30 is 330. So 30, 150, 210, and 330 degrees are all multiple of 30 degrees. Another. For 45, 135, 225, and 315. All of this are multiples of 45 degrees. And for 60 degrees, we will have this one. All of this, there are multiples of 60 degrees. So 30, 45, and 60, they are considered as special angles. Now, let's plot this in one Cartesian plane, and we will give its corresponding radian value. So, this one, 30, 45, 60, 90, 120, and so on. Now, take note, 0 is just the same as 360 degrees, or that's 2 pi. 90 is pi over 2, 180 is pi, 270 is 3 pi over 2. Now, for 30 degrees, that's pi over 6. Its corresponding standard in second quadrant is 5 pi over 6. And third and fourth. And for 45, it's pi over 4. Second quadrant is 3 pi over 4. This is 5 pi over 4. And this is 7 pi over 4. Well, for 60 degrees, it's pi over 3. That's 2 pi over 3. This is 4 pi over 3. And of course, this is 5 pi over 3. So take note, these are the different special angles sketched in one Cartesian plane. Or one unit circle, I mean. So that would be all about angles and angle measures. Thank you.